There we are. Looks like our online friends are with us. We're on page 280, exercise 5.4. And as I said before, there are so many topics in this chapter that you need to take good notes. And I know this might sound strange to some of you, but here you are paying money to learn math. So you might as well learn as much math as you can. And when the book only gives a couple of practice exercises, that's probably not enough to fix it in your mind. So what you do is, after you've worked it and you come back later to look at it again and go, I'm not sure I understand that, then do those same problems over again just to fix it in your mind. And if you don't know why something happens, or if you don't know what to do, you come and ask a question and I'll show you how to do it and help you make sense out of it. And that's what I'm trying to do here on page 280 in problems 1 through 4. They want me to write each number in expanded notation. And if you just look at that number and then start writing it in expanded notation, you'll probably make a mistake. So here's what I do to avoid making a mistake. I put all of these little place values up above the numeral. 3 is 10 to the first. 0 is 10 to the 0. 2 is 10 to the negative 1. We're looking at problem number 2. 9 is 10 to the negative 2. 5 is 10 to the negative 3. And 9 is 10 to the negative 4. Then, when I expand it, I come down here and I go 3 times 10 to the negative 1 plus 0 times 10. Now, I put that down here because in the answer book, they're not going to show the zeros. What's 0 times anything? Just 0? So they're not going to write that in there because it's nothing. But if you have it written in there, it's still not going to be wrong because 0 times 10 to the 0. Does everyone know what 10 to the 0 is? Any number to the 0 power is 1. So that's 0 times 1, which is 0. So then it's 2 times 10 to the negative 1 plus 9 times 10 to the negative 2 plus 5 times 10 to the negative 3 plus 9 times 10 to the negative 4. So I put the zeros in there so I don't lose track of these place values. Okay? So let's look at number 4. 4.30008. So under 4 is in the 10 to the 0 place, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, 10 to the negative 4, there it is, and 10 to the negative 5. So when I expand it, I go 4 times 10 to the 0, which is 4 times 1. If you saw that in the answer book, you would know that's the same as 10 to the 0. 3 times 10 to the negative 1. Plus, and see, I leave out all those zeros, 8 times 10 to the negative 5. So that's the way you'll see it in the answer book. Number 6. Now they give me expanded notation and tell me to write it in standard decimal notation. So for number 6, I go 4 times 10 to the second. Now, see, they left something out. They have 4 times 10 to the second. Then they have plus 5 times 10 to the 0. Well, I'm going to put this other one in here. Plus 0 times 10 to the 1. You see why I'm putting that in there? So I won't lose my place value. And then number 6 says 5 times 10 to the 0 plus 6 times 10 to the second. Well, they've left this one out again. So I'm going to put it in there. 10 to the 0, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, 10 to the negative 4. And see, they left this one out too. So I'm going to put that one in there. So I'm going to put both of these in there so I won't lose track of them when I'm writing out my decimal numeral. Now, just for those who want to make sense out of this, 4 times 10 to the second is 400. Okay? 5 times 10 to the 0 is 5 times 1, that's 5. 0 times 10 to the negative 1, that's just 0 over 10. 6 over 100 plus 0 over 1,000 plus 9 over 10,000. I wrote this stuff down here, these fractions, because I like fractions. And when I do surveys and ask how many people like fractions, nobody likes them. And I feel sorry for all the unwanted fractions in the world that nobody likes. So I take every occasion I can to show you some of my fraction friends. So the stuff with the fractions, you don't have to do that. I just put that in here to make sense out of it. But now let's go back here. I have 400 plus 5. That would be 405. Then, now you see why I put these zeros in here? Because I need that 0 for 0 times 10 to the first. That's no tens. Then when I come over here on the other side, I have a 0 here for 0 times 10 to the negative 1. And then I have 6. And then another 0 for 10 to the negative 3. And then 9. See why I need those other places in there to know where to put the zeros. And this is how you show your work on this stuff, to show me how you found the answer. Problem number 8. 2 times 10 to the negative 1 plus 5 times 10 to the negative 2. And see, they left out 0 times 10 to the negative 3, and then 4 times 10 to the negative 4. So see, when I look at the problem and I copy it over on my paper to work it, I fill in the missing place values, I put those in there with zeros. And why do I do that? Because this is 0 times 10 to the 0, or it's 0 ones plus 2 tenths plus 5 hundredths plus 0 thousandths plus 4 ten thousandths. And what does that look like when I write it in decimal notation? 0.2504. Number 10. Write each number in scientific notation. Did you read about that on page 272? You say, you didn't tell us to. I know, but haven't you figured out by now that if you read the chapter before you come to class, the stuff we do in class will make more sense? You go, yeah, but you didn't tell us to read it. Well, I didn't tell you to brush your teeth either or tie your shoe before you came to class. It's just like after a while, you start thinking, hey, you know, that would be valuable stuff to do that. It would make my learning easier. So if you haven't read page 272, turn over there and read it while I'm working problem 10. And here's what scientific notation means. It means I write every number as a number between 1 and 10 times 10 with an exponent. That's called scientific notation. So here's 0.372. Well, if I'm going to make that a number between 1 and 10, I'm going to have to put 3.72. You follow me? Because that's scientific notation. So what did I do? Say, well, that's not the same. You move the decimal point. Right, I moved the decimal point one place to the right. So that means I have to take this times 10 to the negative 1. Okay? Because can you see how, watch the thinking here. I made the number larger, didn't I? The numeral, I went from 0.372 to 3.72, so I made it larger, so I have to take it times 10 with some exponent to make it smaller to go back to what it said, and that would be why it's mine to the -1. Because if I put the place values up here, this is 10 to the -1, 10 to the -2, and 10 to the -3. So if I move it over and say it's 3.72, well, that's times 10 to the -1. Then that makes this number right here say the same thing as 0.372. That's not a very good 7. Let's try that again. And that's called scientific notation. So why would you do that? Because when you start working with large numbers, using scientific notation is very convenient. When you're looking at small numbers and you rewrite a small number in scientific notation, you go, that just makes it more complicated. I know, but we're just learning to do it so that we can use it to work some problems. Number 12, 3,453,000. So I'm going to write that as 3.453 times 10 to some power. You follow what I'm doing? I'm going to make it a number between 1 and 10 times 10 to some power. Well, 3.453 is a lot smaller than 3,453,000. So how far did I move the decimal point? See how I've got this little wavy line here? This is how you show your work for this stuff. I have the decimal point is here, and I move it 1, 2, 3, 4, 5, 6 times back to make this number, so it's 10 to the 6th power. Now, do you see what happens? If I take 3.453 times 10 to the 6th power, I'm going to get 3,453,000. You go, how is that? Well, because 10 to the 6th power is 1 with 1, 2, 3, 4, 5, 6 zeros. When I take that times 3.453, I get this number up here, 3,453,000. Okay? So write yourself some notes on how you do scientific notation so you'll know how to do that when it comes test time, because he doesn't give you much practice here. So when you come to take the test and you have to do something from all of these topics on the test, it's just going to all kind of run together if you're just trying to store it in your head. So write some notes out, bring them with you. Number 14, write each number in standard notation. So now they've given me a scientific number, 9.01 times 10 to the 7th. That's scientific notation, and they want me to write it in standard notation. So watch how you show your work on this stuff. Here's how I'll just show you how I do it. I go 9.01, and then I just add a bunch of zeros. Actually, when I see the 7th, watch, I'm just going to add 1, 2, 3, 4, 5, 6, 7. Okay? Just to make sure I have enough there. So now it's 9.01. Well, maybe I should do it this way. 9.01 times 10 to the 7th would be 9.01 times 1, 2, 3, 4, 5, 6, 7 times 9.01. And then that would equal, well, see, this is what that shortcut up there. If you took 9.01 times 1 with all those zeros after it. Multiply. You would get 901. 1, 2, 3, 4, 5, 6, 7. And then you'd have 2 decimal places. So it would be 90,100,000. Is that what I got? 90,100,000. Just by annexing zeros and then moving the decimal point over 7 places. But this is how you can do it the long way. To just take 10 to the 7th and take that times 9.01. And then there's your answer. However you get there, just figure out a way that makes sense to you. Number 16 says 4.02 times 10 to the negative 7. Now, see, that would be 4.02 times 1 over 1 with 7 zeros. You follow me? When you have a negative exponent, that's a decimal. So, using this technique, I go 4.02, and then this time, since it's negative, I know I'm going to put the zeros on this side. And because it was 7, I put 7 of them. Then I'm going to move it, just to make sure I'm doing it right, I'm going to move it 7 times. 1, 2, 3, 4, 5, 6, 7. There's where my decimal point goes, right there. 0.00000402. See what's happened? I take it out of here. 0.00000402. Which is 402 tenths, hundreds, thousands, 10,000, 100,000s, millions. Is that right? 10 millions. 402 10 millions. If you were looking at the fraction. Okay? Scientific notation. Now we're getting to number 18, where we're going to use scientific notation. And what it says to do is simplify. Simplify just means do the math. And what's the math here for problem 18? Oh, and it does say write your answer in scientific notation. And put your answer in scientific notation. Well, look what number 18 says. Let me go back to red here. Number 18 says 0.00741. So, what would that be in scientific notation? 7.41 times 10 to the negative 3. You see how I get that? You say no. Okay, I want to move this over to here. So it's a number between 1 and 10. And how many places did I move it? 1, 2, 3 places. And I made it from this real small number to a larger number. So that means my exponent's going to have to be a negative number. So it's 7.41 times 10 to the negative 3. Okay? Then the other part of 18 is 225. 225,000. Well, what would I do with that one in scientific notation? What would it be? 2.25 times 10 to the what power? How far did I move it? 1, 2, 3, 4, 5. So it's 2, and it was a large number. I made it smaller. So it's 2.25 times 10 to the 5th power. You follow the rationale? Good. Now, how do I multiply these two numbers? Very carefully. No. Now, this is where scientific notation is really cool. You turn on your calculator, and you take 7.41 times 2.25, and you get 16.672. You see that? Just pull your calculator. So see, now I'm working with small numbers where I don't start losing things, or my calculator puts a little E up there and starts messing with me because my numbers are too big for the calculator to mess with internally. And this is a convenient way to write long numbers and have them all right there in one little place to look at them. And then the other thing is I multiplied 10 to the negative 3 times 10 to the 5th. And what do you do when you multiply exponential numbers? 10 to the negative 3 times 10 to the 5th would equal what? You add the exponents, so that would be 10 to the 2nd. Negative 3 plus 5 is 2. So my new number is, except 16 is not scientific notation. So watch what I do. I have to bump it down from 16 to 1.6, which means 16.6725 is 1.6725. 1.66725 times 10 to the 1st. So now I've got 10 to the 1st times 10 to the 2nd. So my final answer is, isn't that beautiful? It just looks like a work of art. 1.66725 times 10 to the 3rd, because 10 to the 1st times 10 to the 2nd adds up to 10 to the 3rd when you're adding the exponents. Well, I can tell you're not really all that excited about scientific notation, are you? Well, if scientists are, they think it's so cool. All right, number 20. 4.9 times 10 to the negative 2. That's already scientific notation. That was nice of them. Times 3.5 times 10 to the negative 1. That's already in scientific notation. Thank you. So I take 4.9 with my little calculator times 3.5, and I get 17.15. And then 10 to the negative 2 times 10 to the negative 3 would be 10 to the negative 1 would be 10 to the negative 3. You follow that? Because you're just adding the exponents. Except 17 is not scientific notation, so I have to do the same thing again. 1.715 times 10 to the 1st times 10 to the negative 3 gives me an answer of 1.75 times 10 to the negative 2. Because you see, when I add 1 plus negative 3, that becomes negative 2. Oh, you have no idea. This is just like driving out in the country when the leaves are changing and looking at the beauty of nature. That's why I circle these answers in red. They're just so beautiful. Number 22. Let's do another one. You need some help with this. Oh, no, you go, well, see, this is what's cool about scientific notation. Oh, they didn't put it in scientific notation, did they? Well, let's just work it like it is and see what happens. Because watch what happens with this one. What's 8 times 3? 24. Everybody agree? What's 10 to the second times 10 to the negative 2? 10 to the positive 2 times 10 to the negative 2? That's just 10 to the 0, isn't it? So, just to show you how I'm doing showing my work here on the paper, so I put the 24 over here and the 10 to the negative 10 to the 0 over here. Then underneath, because now I'm doing division, so what's 24 divided by 24? 24 minus 24 is 0. But 24 divided by 24 is 1. Right? So, my answer is 1. You go, what? Wait a minute. My answer is 1 times 10 to the third. You go, what? That's a negative 3. I know, but watch. Let me change to blue here, or green. Maybe I better use green. No, let's use blue. You guys don't like this stuff. So here's 0 divided by negative 3. When you multiply exponential numbers, you add the exponents. When you divide, you do what? Subtract. So that would be 0 minus negative 3. What's 0 minus negative 3? 0 plus 3 plus positive 3. So that's where we get the 10 to the third. You follow that? So there's your answer. I just think scientific numbers are beautiful. I don't know why, they just touch my heart. Number 24. Oh boy, this topic is full of story problems. But you know what I do with words, don't you? I go from all these words in the book to a few mathematical expressions on a piece of paper so I can figure out how to work it. So number 24 says, Sir Arthur Eddington claimed that the total number of electrons in the universe is 136 times 2 to the 256th. So I just put down what Sir Arthur said, and I don't care who he is. I'm just writing down the math. 136 times 2 to the 256th. It can be shown that 2 to the 256 is approximately 1.16 times 10 to the 77th. So this number becomes this number, doesn't it? You follow that? Use this result to write Eddington's number in scientific notation. Well, 136 would be 1.36 times 10 to the second. Does everyone know how I got that? You say, no, because we didn't do enough of these. Okay, let's do another one. 136 in scientific notation would be 1.36. Remember, it has to be a number between 1 and 10 times 10 to, now what's going to be my exponent? The decimal point was here. I moved it back to here. So I took it from a large number, made it a smaller number. It's going to have to be a positive 2. You follow the thinking? So now I have 1.36 times 10 to the second times 1.16 times 10 to the 77th. What's the answer? Well, I get my calculator out and I go 1.36 times 1.16 equals 1.5776. And then 10 to the second times 10 to the 77th would be 10 to the 79th. So that's all they want me to do. Except you can always take a work of art and make it a little better. See, so this is the answer here. All right, this is the answer. But because the original problems were only working with, see this, 2 decimal places here? Then I show my answer to 2 decimal places. 1.58 times 10 to the 79th. Number 28. United States oil reserves are estimated to be 2.2 times 10 to the 10th. So I just write down 2.2 times 10 to the 10th and say that's oil reserves. Then I go back and read what it says next. We use about 7.2 times 10 to the 9th. So we use, this is how much we use per year. You follow what I'm doing? I'm looking through all these words and just writing down the math essentials because I know I'm going to work with math. How long will U.S. oil reserves last? So now they want to know if these are our reserves and we're using this much every year, how many years is this stuff going to last us? If you have a dozen eggs, now see when you're trying to work a problem, you say, I don't know anything about oil. Well, you don't have to. It's not the oil, it's the math that matters. But when you're looking at a problem, if you're trying to figure out, what do I do? Add, subtract, multiply, or divide. Well, think in terms of the way you live. I happen to like scrambled eggs. So I have a dozen eggs at home, and my wife is going to scramble 3 eggs. I know, that's too many, but you put a little cheddar cheese on those things and they just really taste good. So she's going to scramble 3 eggs every day for me. So how long is my reserve of a dozen eggs going to last before I have to buy some more eggs?
4 days.
4 days. See, when you relate it to stuff that you live with every day. So what am I going to do with these 2 numbers in problem 28? If I want to know how many years, if I use 7.2 times 10 to the 9th every year, and the reserves are only 2.2 times 10 to the 10th, you see how I would divide what we use into the reserve? And what do you come up with? Say, well, I don't know. Well, then go 2.2 divided by 7.2 is this number right here. And then 10 to the 10th divided by 10 to the 9th would be 10 to the 1st. You follow that? Good. So in scientific notation, this would be 3.1. Move it over one place. No, it's it'd be 3.05555. I know, but see, these are all to 2 places. So if I round it off, it's 3.1 times 10 to the negative 1. Because I made it larger than what it was less than 1, so I have to use a negative exponent. And that times 10 to the 1 comes out to be 10 to the 0, which is 1. So that's 3.1. You mean to say when this book was written, in 3 years they're going to run out of oil reserves and we're all going to have to, the gas pumps, gas stations are all closed, we're all going to have to start walking to work, riding bicycles, no oil, no gas? No. Because when the guy wrote this book, that's how much they knew they had in reserve. That must be how much they just have stored in tanks, right? Because the reserve in the ground, every year, what do they keep finding? More oil out there somewhere? So it must be that must be how much reserve they have. Did they say what kind of reserve it is? United States oil reserves. So that must be how much oil we have stored away in these great big metal tanks all over the country. So that means we have enough oil stored to where if the oil cartel in the Middle East decides to jack the price up of oil, we don't have to buy any from them for 3 years while we're negotiating with them to lower their price. And if we don't buy their oil, I mean, who else drives cars like we do? Nobody. If we don't buy their oil, they're probably going to get pretty hungry looking for someone to sell it to, and so the price will drop. Don't you wish the price of gas would go back to what it was when I was your age? 30, 40 cents a gallon? Yeah? Well, would you like for wages to go back to what they were when I was your age? See, you can't have it both ways. I told my grandson, he was complaining about the price of gas. I said, you know, bud, when I worked for $1 an hour, I could buy 4 gallons of gas. Now, you work for $10 an hour. How many gallons of gas can you buy with $10? 4 gallons of gas. Quit complaining. I mean, it's the same. You work an hour to get 4 gallons of gas. I worked an hour to get 4 gallons of gas. They just raised the price and raised your wages. Can you imagine going someplace and working 8 hours and the guy at the end of the day gives you $8 and you say thank you and go home? But on the way home, I could buy 4 gallons of gas for $1 because it was 25 cents a gallon. And my car had 350 horsepower. Broom, broom, broom. Okay, enough of that. Let's keep doing that here. Okay, number 32. Perform the indicated operation. What kind of operation is number 32? When you see a little dash, that means what? Add, subtract, multiply, divide?
Subtract.
Subtract. So I just subtract 0.983 from 18.64. So I'm going to add a 0 here. 3 from 10, I can't do that, so I borrow. That becomes a 3. This becomes a 10. Then that's 7. Then 8 from 3, I can't do that. That becomes a 5. And that becomes a 13. 13 minus 8 is 5. 5 minus 9, I can't do that because that becomes a 7. That becomes 15. 15 minus 9 is 6. And I have 17 over here with my decimal point. You go, where's your calculator? Sometimes I just enjoy doing this stuff. Now look at problem B. I'm glad they gave you this one because now this one says negative 18.64 minus 0.983. So what am I doing? I'm subtracting from a subtraction problem. See, the way you look at this, problem B, is think of a number line. Here's 0, and I went negative 18, and then I'm going to go negative 0.9 more. You follow that? So my answer is going to be over here on the negative side, which means when I have these two negatives and I'm adding them, I'm going to end up with a negative, and then I'm just going to add the two numbers together. 3 and 4 and 8 is 12, and 7 and 9 is 16, and there it is, negative 19.623. All right, number 34. 2.48 times 2.7. I know we could do that the long way, but 2.48. I just don't feel like doing it right now. Times 2.7. So that's why I have a little calculator. 6.696. There you go. So you say, you didn't show your work. Okay, so I used a calculator. There you go. Now, I just told you what I did. Say, can we do that on our homework? Of course you can if you use a calculator. If you do it manually, go ahead and show it, because I think it's cool to see all that borrowing stuff. If you use a calculator, just write down, use the calculator, or put CAL, whatever, just to let me know what's going on. Now, number 34B says negative 2.48 times negative 2.7. What's a negative times a negative? Positive. And then do the math. 38. It's division. So I have a negative divided by a positive, and I know it's going to be negative, don't I? Then I just take 1.8, hit my division button, 0.09 equals 20. That's what it says. Probably ought to work that one twice to make sure I got it right. But I did. Because it's 1 8/10 divided by 9/100, which would be 1 8/10 times 100 over 9. Number 40. Car rentals are $25 a day plus 15 cents a mile. You don't want to rent a car like that. You always want to rent them for unlimited mileage. Then you can drive the wheels off of it and just pay one price. So what do they want? So see, I take the information they give me and I put it up here in numbers so I can see. And this is car rental. Now, what's it cost for 2 days on a trip that was 700 miles? You see where I'm pulling the information out of the paragraph and putting it on the paper? Well, $25 a day for 2 days, that's 25 times 2, that's $50. 700 miles times 15 cents, what is 700? 700 times 0.15, $105. See why you don't want to pay mileage on that thing? You go, yeah, but it costs you more. Okay, so it cost me $40 a day to rent a car with unlimited mileage to drive to Oklahoma to see my family, and it's 350 miles down there and 350 miles max, so there's 700 miles. So $40 a day, unlimited mileage is 40 plus 40 is 80. I just paid $80 to make the trip, and you just paid 155. And then when you're paying 15 cents for each mile you drive, you have to watch where you're driving. Hey, I got this car for 40 bucks a day, unlimited mileage. One time my brother was out in New Jersey and he and some friends rented a car and drove back to Oklahoma for his grandson's birthday party. They were truck drivers and took some stuff out to the East Coast. And then after the party, they all got in the car and drove back to New Jersey. Can you imagine how many miles they put on that car? They rented it for unlimited mileage. And when the people at the rental place at Enterprise got it back and looked at how many miles they put on it, they go, oh no, we're going to have to trade this one in. You've already used it up. 42. A worker was paid $4.50 per hour. So I just put down, paid $4.50 per hour for 40 hours of work. This book was written a while back. An additional $1.50 an hour for everything over 40. See where I'm taking the information from the paragraph and putting it up here so I can work with it mathematically. Then what? How much did he earn in 3 weeks? How much did he earn in 3 weeks if he worked 43 hours, 42 hours, and 45 hours? Now, do you see from this information I have underlined in blue, I can now work the problem. $4.50 an hour for 40 hours is $180. So he gets 180, 180, 180. You with me? $4.50 plus $1.50 is $6 an hour, and that's $6 an hour for 3 hours. So that's 18. $6 an hour for 2 hours, that's 12. And $6 an hour for 5 hours, that's 30. So he has 198, 192, and 210. And what's that add up to? $600. Do you see how working story problems is just a matter of pulling the information out of all those words and putting it on their sheet of paper? So, and this is how you show your work for this stuff. Number 44, a library charges, overdue charge, 10 cents for the first day and 5 cents for each additional day. So the fine was 75 cents. I mean, that's what they're telling me. I'm just writing down what they're telling me. How many days overdue was the book? How many days is what they want me to find? Well, 10 cents for the first day, so 75 minus 10 is 65. Agreed? 65 was the rest of the fine, and it was 5 cents a day, so I divide by 5 and I get 13 days. So 13 days plus this day makes a total of 14 days. See, once you extract the information from the paragraph, but if you just try to hold that stuff in your head and figure out what to do, it's not going to work. 46. Round the measure of 45.49 to the nearest meter. Okay, that's 45.49 meters. Now, when it says round it to the nearest meter, it's not 2, it's 1. To the nearest meter, then is it going to be 46 or 45? It's 45.49. So am I going to raise it up to 46 or leave it at 45?
45.
I'm going to leave it at 45 because it's less than 50. If it was 50 or more, you would raise it up. That's the rule for rounding. So if you don't know your rules for rounding, go back and look at them. The sides 48, the sides of a triangle are measured. Find the perimeter. You know what perimeter means? It means the distance around the outside. So that means I just add these numbers together. And I put zeros in here so I can see what I'm doing. Add them up and I get 1,206. But look what it says for problems 48. Find the perimeter of the lot to the correct number of decimal places. Page 277. You better write down those rules for rounding to decimal places. And here's what the rule says. This number has 1 decimal place. This number has 2. This number has 0. So how many decimal places do I want in my answer? 0. You always show your answer in the least number of decimal places that are shown in the problem when you're adding and subtracting. Now, I don't know if you know this or not. When you were taught to round earlier in life, there's different rules for multiplying than there are for adding and subtracting. If you weren't taught different rules, it's now time to learn them. And we'll learn those rules right now. We'll move down to one that shows multiplication. Number 52. On October 17, 1965, the New York Times contained a total of 946 pages. If the thickness of one sheet of paper, one page of paper, is this thick, to the correct number of decimal places, to the correct number of decimal places, find the thickness of the paper. How many pages? 946. That's an exact number. This is an approximate number because they measured it. But is the paper only printed on one side, or is it on, do you do your homework on both sides of the page or just one side? The paper is printed on both sides. So you have to take 946 and divide by 2, and that becomes 473. So I have 473 pages that are .0040 thick. So what happens when I take 473 times .004? I get 1.892. This number right here, 1.892. But how many significant digits in this measurement here? It's on page 278. The rules for multiplication and division. And my answer can only have as many significant digits as the number that you've approximated that has the least digits. And how many significant digits does this number have? It has 2. It says 40. You follow that? If it said 41, 42, 43, 0 counts for that. So it has 2. It's saying 40. So that means I can only have 2 significant digits in my answer. So the answer is going to be, is it going to be 1.8 or 1.9? I look at this 9 and say what? Becomes 1.9. You follow me? So write down those rules for significant digits and say that's what you use when you do multiplication and division. Number 54. Lionel drove 1,900 miles with 62 gallons of gas. How many miles per gallon did he get? I just divide the total miles by 62, and I get this big number right here. But he had 62 gallons of gas in his car. So, oh, wait a minute. So, rounded to the correct number of decimal places, it would be 31. I can only use 2 digits. But look what it said for 54. This is where you got to watch this guy. Sometimes he says, find the answer to the correct number of decimal places. And then on 54 he says, round your answer to the nearest tenth. Where would be the nearest tenth? Right there. So do I leave it 30.6 or make it 30.7? I look at the 4 and say you leave it 30.6. Because he said round it to the nearest tenth. So you have to read the problem carefully to find out what they want you to do. So how far are you supposed to go here? Stop at 57. And it looks like the rest of these are division problems. Can you tell their division by looking at them? So if you're looking at your homework and saying, I'm not sure whether this problem is add, subtract, multiply, or divide, then stick around and ask a question. I'll be here for a few minutes. I wish you would have had as much fun today as I did. But, hey, have a nice day. See you on Friday. It might not hurt to read the pages for the next topic before you come to class without being sent an announcement, just because it'll help you make sense out of what we talk about.